name is Sean Bergen, and I'm a member of the ComSysNet education team. In this module, we'll review the basics of documentation for your scientific model. Various scientific disciplines use scientific protocols for model documentation, and we will not review all of these approaches here. Instead, we will focus on the general characteristics of good model documentation. Providing model code alone is not sufficient for other researchers to understand and replicate a model. Proper model documentation explains the intention of a developer when they wrote their model code, makes it easier to test it, and easier to use it. Model documentation should describe a model's purpose, assumptions, and describe the data used to create and test the model. Surprisingly, some models are not explicit about their actual purpose. A model is a simplification of reality, so choices have to be made to best answer your own research question. Knowing the purpose helps explain why choices are made in the implementation and simplification of certain processes within your model. For example, here's the flocking model in NetLogo. Was this model made by a biologist studying starlings? Was it made for a company trying to monetize a new secure network of homing pigeons? Or was it created to demonstrate NetLogo and the ways that simple roles of behaviors can lead to aggregate behaviors? In this case, the model was created as a tool for education about NetLogo. But in many cases, the purpose behind the model's creation may be unclear. So, as you explain the purpose of your software, you must record more than just a topic, but also explain if you're attempting to answer a research question, demonstrating a simple concept, or even making future projections for a client. As you describe the purpose of your scientific model, it's important to include relevant background. This information should include a summary of the system or behavior that you're trying to model. This may also include references to information about specific topics or references related to computational models that you or other researchers have authored. There are a few key topics to include in the model overview. What are the main components of the model, and how are they related? What are the key spatial and temporal scales of the model? If you're using NetLogo, what does a click mean to you? Is it a year, an hour, or maybe it doesn't correspond to a unit of time? Is your model located on a real landscape or an abstract gridded torus with little importance to the model? Here, we are looking at an AVM created to understand evictions in the Phoenix region during the COVID pandemic. You might correctly guess that the agents in the simulation represent renting households. There are also aid agencies, which can provide financial assistance to households. But since we were not interested in landlords, they are not included in this model. The model is run on a monthly timescale, since we are interested in renters that pay rent on a monthly basis. Interestingly, even though this model looks like it has an important spatial dimension, it doesn't. Households are located in different townships, but the map is only for visual effect and does not affect the model. Thus, the components and scales of the model are not necessarily intuitive, even when looking at more than the code. A good way to ensure that you fully explain the components and scales of your model is to provide a visual model overview. There are a number of formal approaches to visualizing your model that may be commonly used in your own discipline. Most approaches use different shapes to denote decisions, processes, or the inclusion of external data. For example, this flowchart was used to explain the decisions of a household in the previously mentioned eviction model. As you can see, after they receive their monthly income, households must pay rent and utilities. If they are unable, they may be evicted. While the concept of paying for your rent is not unfamiliar to most people, this flowchart illustrates that agents pay rent after paying for food and before utilities. This sequence of payments is not necessarily obvious and likely impacts the output of the model. Obviously, an overview of your model will not be enough to provide good documentation of your scientific software. The user of your model must understand why certain choices were made so that they can make changes in a meaningful way. You must include the details of key components. For a complete explanation, you may need to use equations or pseudocode. One should list and justify their assumptions, and one must describe the parameters used in the simulation, and be sure to include things like units of measurement, or how the parameter values were chosen. One should also include details of where or how input data was generated. The data should be provided, and if it cannot be, the author may create a fictional data set that can be used by other researchers. Documentation for your scientific software should also include practical information for implementing the software. This includes the platform and language used. This can include an illustrative simulation to demonstrate the model, or this may include an analysis of the outputs of your scientific software. Although many, if not most of us, fail to do so, it is actually best to begin documentation at the start of a project. One, keep a document detailing changes you have made, assumptions, or how certain parameter values were chosen. This document need not be published, and in fact, it's probably best if it's considered independent of academic publication. This information could be included later as an appendix, or as a document that is included with when the software is archived. If you wait to document your scientific software until you are finished, many of the important details may be forgotten, or you might even have to search for your data sources again. Where did I download the map I used? How did I figure out the evapotranspiration rate of soil in the area? The development of scientific software is rarely quick or straightforward, and treating documentation as a continuous process is essential. In the next module, we will consider the importance of software licenses and how to choose a license for your scientific software.